Hi, I am Minting Song from University of Maryland, and today I'm going to present our paper titled Efficient Topology-Aware Simplification of Large Triangulated Terrains. This is a joint work with Ricardo Vergara, Federico Urcic, and Leila Di Glorini. The increasing availability of massive point cloud data collected directly from the Earth's surface motivates the need for efficient techniques to handle them. One of those techniques is the triangulated irregular networks, which we usually refer to as TINs. TINs can be used to connect point clouds and to model terrain surfaces. Compared to raster-based terrain models like DEMs, TINs are more suitable for irregularly distributed data like LiDAR point cloud data. However, their usage is limited by their large storage costs. One way to solve that is to use mesh simplification to reduce the size of a TIN in order to accelerate or enable further processing. For example, several simulation dynamic models rely on quality and computationally efficient triangle meshes for representing the terrain surface. Therefore, they usually include mesh simplification as one of their pre-processing steps. However, mesh simplification may affect the topology of the underlying terrain and also affect the result of terrain segmentation. This is undesirable in many simulation applications. To solve this issue, we can use topology-aware mesh simplification, which is to simplify a TIN while preserving the topology of the underlying terrain. The topology here is defined as critical points on the terrain and their connectivity. Those critical points represent important features on the terrain surface, like passes, peaks, and valleys. To summarize, the limitations of existing methods is first, most of them do not consider terrain topology. And secondly, when handling large meshes, which is common in current research and applications, the simplification is memory demanding and time consuming. This is even more evident when we do topology-aware mesh simplification, since we need extra time and space for handling topology. To address those issues, we introduced a new algorithm for efficient topology-aware mesh simplification. We use a compact and modular data structure called terrain trees. Based on this new algorithm, we also extended it to a parallel version relying on the hierarchical decomposition of terrain trees. The source code of those two algorithms are publicly available on GitHub. So if you're interested, you can go to this link and find the source code. The topology of terrain can be described by the formal gradient field, which is based on the discrete Moore theory. Discrete Moore theory relies on a scalar function defined over the TIN, and in terrain analysis, this scalar function can be derived from the elevation function. A formal gradient field has three components. First, it has a collection of gradient pairs, which can be vertex-edge or edge-triangle pairs. Consecutive gradient pairs form gradient paths, which do not contain cycles within the formal gradient field. A simplex that is not in any gradient pair is called a critical simplex, and there are three types of critical simplexes on a TIN corresponding to three important features on terrain surface. They are minimum, saddles, and maximum. Therefore, a topology-aware mesh simplification should maintain all the critical simplexes while ensuring that the gradient paths are still consistent after the simplification. Our work is based on the data structure called terrain trees. Terrain trees was firstly introduced in our work in 2017. They rely on a nested decomposition of the domain into non-overlapping blocks. Each block encodes a list of vertices and a list of triangles. Terrain trees requires 6% less storage compared to the IA data structure, which proves that they are very compact and are suitable for our simplification methods. The basic paradigm of algorithms performed on terrain trees is that every time we take one block from the terrain tree and process it. For each block, local application-dependent data structures are generated, used in the process, and then discarded after the processing. Based on data structure, we have developed also a library called Sequential library. This explores several queries and feature extractions, and it is also publicly available on GitHub. Our topology-aware simplification relies on a gradient-aware edge contraction operator. Edge contraction contracts an edge to one of its endpoints, and when we do simplification without considering the topology, we use quadratic error metric, link condition, and fault condition to ensure the mesh quality after the contraction. The difference between gradient-aware edge contraction to a normal edge contraction is that we should also consider the gradient condition. The purpose of gradient condition is to ensure that no critical simplices is introduced or removed during the contraction. And also, we should update gradient pairs after the contraction to keep the gradient paths consistent. Using the gradient-aware edge contraction operator, we define our sequential topology-aware simplification algorithm. As I mentioned when I introduced terrain trees, a procedure on terrain trees is done block by block. So in our sequential algorithm, we do the following steps to each block of a terrain tree. So first, we extract necessary connectivity relations for the simplification and the update. Then we build a priority queue of all edges with at least one vertex located in the current block. From this priority queue, every time we take one edge and check if it satisfies all three conditions I mentioned earlier. And if it satisfies them, then we contract it. After contracting one edge, the foreign gradient, the terrain tree, and the mesh should be updated accordingly. And the last two steps, the simplification and update, are repeated until there's no edge in the priority queue. Based on the sequential topology-aware simplification, we extended to a parallel version. The idea we have here is to simplify different parts of the mesh at the same time on different threads. And thanks to the decomposition of terrain trees, this problem is converted to simplify different blocks of terrain tree at the same time on different threads. The major challenge here is to avoid write and read conflicts between those threads. For example, when two edges are adjacent to each other and being contracted at the same time, there will be a conflict during the condition check and the update, like we show in the left figure here. Even if two edges are not adjacent to each other, like we show in the right figure, the contraction of edge E and the edge E prime can still cause a conflict, since the gradient information of the yellow triangle here can be modified due to the contraction of both edges at the same time. To avoid that, we define the concept of conflict blocks. When two vertices of an edge belong to two different blocks, then we call those two blocks conflict blocks of each other, since they are connected by this edge. We require that when the block is being processed, none of its conflict blocks can be processed at the same time. Therefore, we can avoid the first types of conflicts. When two edges are adjacent to each other, then they cannot be simplified at the same time. We also require that when two blocks share a conflict block, then they cannot be processed at the same time. This helps to avoid the second types of conflicts when two edges are not adjacent to each other, but may still affect each other's contraction. Using this strategy, we can avoid conflict during our parallel simplification. To evaluate our methods, we compare our sequential topology-aware simplification to the topology-aware simplification on the IA data structure. The IA data structure is the triangle-based global data structure, which relies on a global queue for the simplification. From the comparison, we find that using a local queue, like we did in terrain trees, or using a global queue, like we did in the IA data structure, does not clearly affect the simplification ratio. The difference is about 0.5%. We also find that the simplification of terrain trees leads to 41% less memory cost, 45 to 56% less time cost compared to the simplification on the IA data structure. The same conclusion holds when we use different cost threshold and when we contract different numbers of edges. We also We also compared our parallel version to the sequential version on terrain trees to evaluate our parallel mass simplification algorithm. From the comparison, we find that the parallel simplification method can reach 12 times speed up compared to the sequential version when we use 20 threads, which is also the number of cores of our workstation. When the number of threads exceeds 20, the speed up can increase slightly, but the efficiency decreases sharply afterwards. Therefore, we draw the conclusion that in our application, the optimized number of threads should be the same as the number of cores in our workstation. We also find that the memory cost and the simplification ratio does not change significantly compared to the sequential version, and they remain stable when the number of threads change. The memory is only 1% more compared to the sequential version, and the simplification ratio is only 0.1% less compared to the sequential version. To summarize, in our work, we propose a new topology-aware simplification method, which requires less time and less memory compared to topology-aware simplification on a global data structure, like the IA data structure. We also extended to a parallel version, which can reach 12 times speed up on a 20-core machine. This parallel strategy can be extended to other topology-aware edge contraction operators, since the range of simplices getting involved is same. Our future work will focus on using specialized compilers, other libraries, or distributed memory strategy to further enhance the computing efficiency. We also want to apply this method to real-world problems like CI surface modeling or storm surge simulation. At the end of my presentation, I want to thank the support from National Science Foundation and German Aerospace Center. That's all for my presentation. Thank you for listening, and I'm happy to answer your questions.